All right, so we're going to talk about screws today. Before we talk about screws, topics for review so far. These are my review topics that I've heard. I've heard 3D equilibrium. I've heard non-rectangular distributed loads. And there's one more. Yes, thank you. What do we want to call that? Moment about a specified axis. Okay.
Will we ever have to do a shear moment diagram or just friction too?
No. Okay. Any other topics that you want to see on Wednesday and Friday? What's that? I can't hear you, I'm sorry. Oh, okay. So I think that's non-rectangular distributed loads. You mean like when you have a triangle load on something? Yeah. Yep. No, you're good. Ooh, yes, complicated frame or machine. Complicated frame or machine. That'd be good. Couple moments. Okay. All right. Okay.
What's going to be, like, out of the stuff that we learned since the last midterm?
Yeah.
What's going to be on the final? Like, is it going to be like a screw problem or like a combination of them?
Yeah. So the question is, out of the content that we've learned since the last midterm, what will be on the final? Friction will certainly be on the final. And so you want to know if screws will be on the final specifically. Let me think about that, and I'll let you know on Friday. Okay. But friction will definitely be on there. I think that's pretty much all we've covered since the last midterm, right? We got broken up by Thanksgiving and all sorts of stuff. So, what did you say? Veggies. Sorry, I didn't hear you. Veggies. Yes, veggies will be on the final probably. Okay. Maybe I'll just give you one giant singular problem that involves a veg, a screw, a truss, a beam. Oh, that'd be awesome. I would love that.
Do you really want to like design that problem?
I do. I do really want to design that problem. I think it would be interesting. It could be. Maybe I should. Maybe that's right. Maybe I should do it not as extra credit, but as like a study guide. If you can solve everything on this, that'd be cool. All right. So screws. We're going to talk about screws today. We're not talking about screws in the sense of using something as a fastener. Fastener. That's not what we're talking about. We're talking about screws like as a jack. Yeah, lifting or moving things, right? So if you have a car and you get a flat tire, how many of you could change a flat tire on your own car? A little show of hands. Okay. So homework over the break, you need to learn how to change your own flat tire. I don't care if you have a dad that you'd call, you need to learn to change your own flat tire. It is not rocket science, agreed. Okay? Nope. Nope. You can't pump air to it. There's not air compressors on the side of the road everywhere. You need to learn how to change your own tire. Get out the owner's manual for your car. It'll tell you how to do it. If you don't have an owner's manual for your car, get on Google and get an owner's manual for your car and figure out how to change your own tire. This is like life skill. You should not be able to graduate from college and not know how to change your own tire. It's a fundamental belief of mine. What's dooming society is that nobody can change their own tire. They always call someone who can. It's ridiculous. Okay? So if you do that, if you look in your car, you're going to find a jack. And it is not a hydraulic jack, which is a pretty cool device. It's a screw jack, because that's a whole lot cheaper to manufacture than a hydraulic jack. Okay? How does it work? Well, there's a couple different ways that it can work. One is, it can look like this. Okay, and these are all 2-force members, and then you've got a screw that goes across here. Okay, and this screw has threads. And then you got a crank that you put on here. Okay, and you turn this guy. And as the screw pulls these together, what happens? The jack goes up. And as the screw pulls them apart, it goes back down. Okay, and this is all predicated on using a screw. But how come when you jack it up, it doesn't fall down? Because the threads are holding it? Is that what you said? Friction! Ding, 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 ding. Exactly. Friction. I wish I could do a good Bob Barker impression right now. Bob Barker. How many people know who Bob Barker is? Okay, if you don't, you need to watch Billy Madison, because that explains who Bob Barker is. Billy Madison? Shut up. Wow. Bob Barker was the original host of The Price is Right before Drew Carey. Yes. Okay. So, so before he was born, right? Yes, Billy Madison came out before you were born. Yes, I feel old. Okay. So the jack functions, it's a good thing that we have friction in this case, right? It makes it harder to move the jack up, but it means that we don't have to stand there the whole time holding it, right? Because that would make changing the tire incredibly difficult by yourself. If you had to hold the jack up with one hand and undo the bolts on the wheel with the other hand, that would suck. So you design this so that it's what's called a self-locking screw, meaning that the friction is sufficient to hold this thing from backing off. This is one style of screw jack you might see. There's another style. I think this is what I have in my truck. It looks a little bit like a bottle jack. And I haven't actually taken one of these apart to know exactly how it works. But it's got a little case like this. And then there's a little knob on the side that you turn that somehow turns the screw in here. And here the screw goes up like that. Okay. Either way, screws are very helpful. We use them a lot in trying to move and adjust things. Mechanical engineers get all excited about screws. Okay? Using them not as a fastener, but using them to move things. So how do we analyze the friction that's going on here? It turns out that a screw, if we look at it, I'm going to draw a close-up of a screw. Okay? And if we looked at this, we could say that the screw has threads, right? And that the threads are usually at a diagonal, sort of like a barbershop light, right? And the way a screw functions, maybe I'll make this a bolt. Here's the head of the bolt, right? And if you turn this guy, it typically mates in a nut or some threads, right? So what happens is that there's something that rides along here. There's a corresponding set of grooves that kind of go in between these, right? And so if I turn this if we're looking at the top and I turn this clockwise, it's going to go in. If I turn it counterclockwise, it's going to come out. Can everybody kind of see that? Righty-tighty, lefty-loosey, right? So what I want to look at, though, is if I looked between these two threads, right, this is where the two threads contact, right, in this area. Okay, they contact all the way along here. They'll there and there and there. Where there's that contact, it's sliding back and forth depending on which way I'm going here. And we know that there's some friction. So the idea is if I put my car on top of this bottle jack, maybe I have a heavy car. Let's say I have 3,000 pounds on the bottle jack, right? I'm just lifting the front corner of my truck, and I bet it'd be reasonable to assume it's 3,000 pounds, right? I have a big diesel engine sticking on top of it. So maybe there's 3,000 pounds acting down on that. So if I put that here, I have 3,000 pounds acting down, and then I'm going to have some normal then by the threads that are pushing back for that to be in equilibrium. Well, that means there's a whole lot of normal on this slipping joint here. And it turns out if we just zoom in, okay, here's a little picture, I zoom in bigger on a bolt. Now I'm going to zoom in just on this, and it looks a whole lot like I've got a veg or a ramp, right? And then on this ramp, I could treat all of the threads that wrap around this, I could treat them all as a box. Okay. And I could say that I have my 3,000 pounds acting down. We know that we'll have a normal that's always normal here, right? And now it depends on, am I trying to raise this or lower it? So let's start with the case I'm trying to raise my 3,000 pound load, and I do that by twisting on the screw. Okay, so let's look at I'm going to do a bird's eye view for a second. If this is, oh shoot, I already screwed up, but that's okay. I drew an octagon instead of a hexagon, but if this is a bolt, and I stick a wrench on it, okay? And I'm trying to bring this bolt towards me, so I'm going to pull it in that direction. I apply some torque, right? And that torque, maybe we'll say, I ate my Wheaties this morning, 100 foot-pounds. Okay? I apply 100 foot-pounds, and on this wrench. Okay, so that means that that's the same thing as having 100 foot-pounds right here, right? Because what I'm showing is a couple moments. So I'm twisting it with 100 foot-pounds. So then I need to know, well, what's the force pushing this up? Well, it'd be the 100 foot-pounds if the diameter of the threads here, right, I'm going to call that R. So if I take that moment and I divide it by R, that would give me the force that's acting there. Right, so what I'm saying is if I have 100 foot-pounds of twist, and that is caused by the friction or whatever that's right on the surface of the 1/4-inch diameter bolt, then I'm, let's say it's a 1/2-inch diameter bolt, so a 1/4-inch radius. So that means that 100 foot-pounds is 0.25 inches times whatever F is. Is F going to be a big number or a small number? Big, giant number, right? So 0.25 inches is, I think that's 1/48 of a foot. Right? Anyone want to convert a 1/4 inch? Pretty sure there's 1/4 inch would be 1/48 of a foot. It's 48. Okay. So could someone figure out what F is in this case? Yeah, thank you. Brendan does math in his head well, and he says it's 4,800 pounds. Is that right? 4,800. Yep. Yep. Okay. Right? Does everyone understand where the 4,800 pounds comes from? Why it's, if I say there's 100 foot-pounds here, I take the moment and I divide by the radius of the screw to get the actual force that's moving it up and down. Yeah, so let me try a 3D drawing. This is going to get a little different. Right? Here's the screw, okay? Or the bolt. And we're saying that we've put 100 foot-pounds on this. Okay? We're also saying that the bolt has a diameter of 0.5 inches. Okay? So that means that it has a radius from the center to here of 0.25 inches, right? Okay? So this bolt is free to spin, except if I'm putting 100 foot-pounds on it and it's in equilibrium, that means that there must be a frictional force, right, that's acting out on the surface of the bolt that's going to the left, counteracting that. Okay? And so essentially what I'm saying is we want to find what is F such that it counteracts the 100 foot-pounds. So if I sum the moments about the axes and say they have to be equal to 0, right? I'm going to say, okay, looking down from the top, I have 100 foot-pounds minus F times whatever R is equals 0, right? Does that make sense? So then I can say, oh, F is equal to 100 over R, which is really just the moment over the R. Okay? And so when we're doing the free body diagram of our veg, right, then we know we have 3,000 pounds, the weight of my truck, acting down on it. We know we have some normal from the ramp. We know the force pushing it, if we were saying that we're going to lift the truck up, is M over R, and we're missing one other force. What is it? Yeah, we have, which way is impending motion occurring on this block? Yeah, it's going to be counteracting this force. So we're going to have some force of friction there. Okay. Now, what do we know about our ramp here? If we were to look at the threads of a screw, we're unraveling them. And we could determine, you know, it matters what this angle is here, right? This angle, let's call it theta. That's the angle of our ramp. How could we find the angle of the ramp that is actually just a thread that's unwound from a screw? What do we know maybe in one revolution of the screw? So if I unwrap this, right, in one revolution, I'm going to go from here to here. Oh gosh, that was horrible. Okay, so I'm going to call that the height. I'm calling it L, but because that's following the how your book lays it out, but we're going to call that the height. Okay. How about the distance you travel along the ramp? What would that be? The width of the screw? Circumference of the screw, right? Because it goes all the way around. It goes. My ramp is going to start here and go all the way around until you get to the end, right? So this is going to be 2 pi r. Right? So we can find theta then. Theta will be the inverse tangent of what? over 2 pi r. Okay? So a screw is really just a wedge that's wrapped around a cylinder. Okay, so maybe that's a better way to approach it. Rather than saying, let's start it at a screw and work our way back to how it's a wedge, let's start at a wedge and say we take a wedge and we wrap it around a cylinder, okay, and now we have a screw. So if we take a wedge, what would the length of the wedge be that it requires to go one revolution around that screw? Well, it's 2 pi r. It's the circumference. How much height does that change? Well, that'd be what's called the thread pitch, right? How far you move with every revolution of the screw, okay? That would give us the L. So here's a funny thing. I'm going to redraw this so that we have it all nice and pretty because it's getting kind of cluttered. Okay. All right. Now, I'm going to go ahead and combine my force of friction and normal into a single resultant force. If I were to draw a line going straight down, would you agree with me that the normal is going to be theta? The angle between the normal and the vertical is theta. Okay. And I'm going to call phi the angle between that resultant and the normal. And looking at this, we could see that phi, the angle phi, is going to be equal to the inverse tangent of the force of friction over the normal. Right? You all right with that? Because the resultant here is a combination of the force of friction and the normal, right? So what I would be doing to add these together is I would move the force of friction down here. And now we could see, okay, the tangent would be the force of friction over the normal. That'd give me the angle phi. But recall that the force of friction, what is the force of friction when we're about to cause motion to happen? Excuse me? The force of friction when we're right about when slipping's about to occur. Mu static times normal, right? Good job. Hey, wait a second. These guys cancel, and phi becomes just the inverse tangent of mu static. Okay? Now, let's do our equations of equilibrium on this. We'll sum the forces in the x and set them equal to 0. So it looks to me like I have m over r minus r, the resultant, And we're going to say times the sine of theta plus phi equals 0. Right? Because if theta and phi are here, I'd take r, and I would want the opposite of that. So that's the sine. Is everyone okay with that? Well, I'm using sine there. Okay? And now I can sum the forces in the y direction and set that equal to 0. Looks like I'll have r. It's going to be cosine theta plus phi minus 3,000 equals 0. Okay. Now we can eliminate some stuff, and we come up with the generic equation for determining the torque required in order to move this screw, because we can cancel out the r. I can never remember what that equation is. I don't know. I'm going to look it up in the book in just a second here. But the reason I'm doing it this way, rather than just giving you the equation, is because I want to make 2 points to you. One is that a screw is simply a wedge wrapped around a cylinder. Okay? So if you can figure out how much you move up or down in one rotation, that tells you the height of your wedge. If you know the diameter of your screw, that tells you essentially the length of your wedge. And you can draw this problem as a simple inclined plane. Right? And so that makes it much easier. So if you forget, say on a final, what the equation is for the torque required to move a screw, that's not a problem for you because you're a good student, and you can just go ahead and draw the wedge and solve it. Okay? Oh, the veg. Sorry. Yeah. So let me show you here. What we've just looked at is the case where we're trying to lift the 3,000 pounds, right? So what we just did is on page 432 in your book, and we just wrote these equations. Okay, the only difference is I put in that my truck weighed 3,000 pounds. If we eliminate the r in these two equations, what we come up with is that the moment required to turn that screw is going to equal the radius of the screw times the weight you're lifting times the tangent of the angle of the ramp plus the angle of static friction. Okay? So let's put that. What we're doing is we can combine these two equations. Let me see if I can get this so you can see. There we go. We're combining these two equations to say that the moment, what we're trying to solve for, is equal to r times the weight times the tangent of the angle of the ramp plus the angle of static friction. Okay? This moment, exactly, is the amount of torque required to turn the screw and cause it to start lifting the truck. Okay? Phi static. So this is the angle of static friction. Okay, so let's try this. Let's go back to our example. We know I've said that the truck weighs 3,000 pounds. Okay? Let's say that the screw in my jack let's say the screw has a diameter of 1 inch. Sorry, a diameter of 1 inch. Okay? And that for every, it has, let's say it has 10 TPI. Anybody know what TPI means in threads per inch. Nice. Okay, so that means that in 1 inch, of height of the screw, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 threads. Okay, so what's the pitch then? If I have 10 threads per inch, how much do I move with 1 revolution? 1/10 of an inch. Exactly. Okay, so if I have 10 threads per inch, that means if I turn the screw 1 time, it's going to change its height 0.1 inches. Okay? So for every turn of the screw, my truck's going to go up 0.1 inches. We know that the screw has a diameter of 1 inch. So that allows us to figure out L in this case is 0.1 inches. The length of the ramp is going to be 2 pi times 0.5. Okay? So 2 pi is 6.28. Well, it's just pi then, I guess. 2 times a half is 1, so it's just pi. So it's 3.14 inches. Right? So the height of my wedge is 0.1. The length of my wedge is 3.14 inches. Okay? So how can we figure out what theta is? Theta is going to be the inverse tangent of the height, 0.1, divided by the length, 3.14. Someone tell me what that is? Not a very big number. 1 point what? 82 degrees. Right? And let's say that somehow I'm able to determine that the mu static for this guy is, let's say it's 0.25, right? The coefficient of static friction is 0.25. So if I know that, I can figure out phi, because phi is equal to the inverse tangent of mu static, right? That's what we determined over here. So what's the inverse tangent of 0.25? 14? Is that what you said? 14 degrees. Okay? So the moment to lift my truck is going to be the radius of the screw, 0.5 inches, times the weight I'm lifting, 3,000 pounds, times the tangent of the angle of the ramp, 1.82, plus the angle of static friction, 14. What's the moment required? $425 foot-pounds? Yep. Okay. That's a lot. You don't think I'm going to turn that bolt? So how could I decrease this number? Increase the length of the ramp? Oh, increase the handle length? Yeah, so if I got a big, long lever arm, I could do that. But what other knob could I turn? Let's resolve the problem and say I change it. I oil my jack. And I can drop the coefficient of static friction to 0.1. How does that change things? Well, it would change this. The inverse tangent of 0.1 equals what? 5.7. Okay. So resolve this, where we substitute in 5.7 degrees for the 14. What's my moment then? Okay. Just a second. This isn't actually, I was thinking, wait, something's not adding up here. And Joseph just cued me in on what it is. Who can tell me what's wrong here? Lance has got it. This should be inch pounds. Where did I get my feet from? Inch pounds. 425 inch pounds? All day, every day. No problem there. Right? 425 inch pounds. That means 425 pounds at 1 inch, or 1 pound at 425 inches, or, but 425 inch pounds, let's divide that by 12. It's, excuse me? 35 foot-pounds. That I can do, right? I can put 35 pounds 1 foot away from this screw, right? I can lift my truck. Strong. 3,000 pounds, no problem. I'm a mechanical engineer. Ha! Right? If it's good enough for the Egyptians to build pyramids, it's good enough for us, right? Okay? Screws. All right, I'm going to give you another problem then. Let's think about this. All right, this is a C-clamp. Okay? These things are built for smashing stuff. Okay? Or holding stuff. But how does it hold it? By smashing it. That's right. Okay? So, let's say this is a 6-inch C-clamp. That means it's got a 6-inch throat, or a 6-inch opening. And does that matter for our analysis of how hard I can squish? Not a bit. Okay? What is going to determine how hard I can smash here? Yeah, the screw. What else? The pitch. Okay, so the threads per inch. And I'm going to say that I'm going to apply a load of 30 pounds to this here little lever. Okay? And that lever, I'm going to say, is 4 inches long. Okay? So the length of my lever there matters for how hard I can squish. Okay? So I'm going to tell you that the this screw has a diameter of 1/2 inch, and it has 20 threads per inch. And what I would like you to find is how much clamping force can I generate? Okay? Go for it. Ah, I'm missing one other thing. What am I missing? What else do you need to know to solve this? Mu. You need mu static. I gave you the diameter, and so I'm hoping at this point in your education, this is the diameter symbol. Sorry. Yep. It's a little circle with a slash through it. That means diameter. Oh. Shoot. Phi is a Greek letter. Nope. I understand your confusion around phi and the diameter. I'm sorry, I will stop using them. The diameter of this is 0.5. Mu static is the coefficient of static friction. Phi, right, is the friction angle. You're welcome, buddy. So the question is, for the force acting on the lever arm, are we assuming that to be M or W? So the force acting on the lever arm, by the fact that it's acting on the lever arm, can create a torque or a moment, right? So, no. Because so W is the clamping, is the smashing force, right? M is the moment you apply to cause that. So here we can figure out that we have 30 times 4, we have 120 inch-pounds as our moment that we can apply. W is our unknown. We're trying to find W. So we know we have 120 inch-pounds is equal to the radius of the screw, which is going to be 0.25, times our unknown W, times the tangent of theta plus phi static. Anyone come up with a value?
6,059.
So we're going to use our equation M equals R W tan theta plus phi static. We know that M is 30 times 4, 120 inch-pounds, is equal to R, which is going to be 0.25 inches, times W, my unknown, times the tangent of theta. Okay, well, we need to figure out what theta is. So theta is going to be the inverse tangent of 20 threads per inch, means that we go 0.05 inches per revolution. That's the height of our wedge. The length of our wedge is going to be 2 pi times 0.5. No, 2 pi times 0.25, excuse me. Right? It's 2 pi r. It's 1.82. Okay. And then the friction angle is going to be the inverse tangent of 0.2, which is 11.3 degrees. Okay. So what did you say you got? 2,059 pounds. Okay. That's how much you can squish. Yes, sir. How did I get L? And by L, do you mean the height of the? Yeah. So the way I got that is that I'm told that it's 20 threads per inch. So that what that is telling me is that if I look at my screw, in 1 inch, let's say this is a 1 inch section of screw, there's going to be 20 threads. I didn't count them, but let's say that's 20 threads, okay? That means that each wedge causes you to go 1/20th of an inch, right? Because there's 20 wedges that add up to 1 inch total, because there's 20 threads per inch. So you go around it 20 times in 1 inch, and when you, yes, it takes 20 rotations to move the screw 1 inch. So that means each rotation moves it 1/20th of an inch. Does that make sense? So then 1/20th of an inch is just 0.05, or 1 divided by 20 is 0.05. Okay?
You know the wedge image, or the representation at the top that looks like a wedge? What is the dotted part of the wedge doing? Like making it a triangle like that?
Yeah, so the question is, what is the dotted part of the wedge doing here? Excuse me, I'm going to sneeze. Thank you. Wow, that was exciting. The question is this horizontal dotted line. Why is that there? That's there because it tells us that is the horizontal, and that's the angle from which the theta is taken. Right, so this dotted line would be perpendicular to the screw. The reason the wedge is up and tilted like this is because if you think about it, it should actually be not tilted, but it should be more like a constant thickness that goes down like this, right? Because the thread has some thickness to it, but then the thread below it starts to cut into the wedge. Here, maybe, so a really, really big screw. We used to have a really, really big screw in here. So if these are threads, you can see they're tilted, right? And if they were thinner, these ones are really thick. If the thread itself was thinner, and I took a slice across it, you would see that that it would cut into my slice, right? So let's say that instead of being as thick as this is, the thread is pretty thin, right? So now if I drew a horizontal line across, see how the thread would be going up, and that's what we're trying to,
What that line is, the line is horizontal.
yeah, the horizontal line is horizontal, and then this is kind of the bottom of the wedge or the thread as it goes up. Yep. Okay. So we've figured out that we can apply 2,059 pounds of clamping force on this when we tighten it, right? And that's based on having a mu static of 0.2 and 20 threads per inch for the thread pitch. So what about untightening it? What about loosening it? Will it take 30 pounds to loosen this clamp? Will it take more or less than 30 pounds or 30 pounds exactly? What do you think? Okay, everyone seems to feel like less. Why do you think less? Okay, you're not pushing into something. The natural force of the thing that you're clamping is pushing back. Okay, that's an interesting idea. Maybe you're reducing the amount of friction. Think about which way I'm pushing the block. Am I pushing it up the hill or down the hill now? Right? So when we're tightening, we're shoving this up the hill. We're pushing that up the ramp. Okay? When we're loosening, we're pushing it down the ramp, which should inherently be easier. Right? So pushing it down the ramp is going to be easier than pushing it up the ramp. And so let's keep looking at this problem with the C-clamp. Well, actually, maybe, so we've decided that it's going to be easier to undo, but how about this? What if we just leave it sitting there? Will it stay clamped or is it going to unwind? And how do we know? It depends on if it's self-locking, right? So a self-locking screw is one that I can apply this 30 pounds of force and get my 2,059 pounds of clamping force, let go, and it doesn't unwind, right? When does that happen? Okay, that happens whenever the static angle of friction is greater than the ramp angle. Okay, this means self-locking. So is that true in this case? Yeah. 11.3 is much, much greater than 1.82. Okay. So let's draw our free body diagram then. This is our ramp. So we're saying we have 2,059 pounds of clamping force. We're going to have some normal, right? We're now going to unclamp it. So that means that we're going to put some force M over R on the side, which then impending motion is going to be this way, or is going to be opposite it. So force of friction becomes here. And our R is right here. Okay. R is not straight up. R is canted a little bit this way. Okay. So let's think about this for a second. We know, let me put a straight up line for you on here. There's my straight up line. Does that look straight up to you? Oh man. Okay. This is still theta. Right? Where's phi going to be? Between R and normal. There's phi. Right? And so you can see that it's self-locking as long as phi is greater than or equal to theta. And I'll put an S on this so that we know this is not the diameter, but it's the angle of static friction. So as long as the angle of static friction is greater than the angle of the ramp, we're going to have a self-locking screw. How do you know where R goes? So you could find it by finding phi, or you can, R is just the combination of the normal and the force of friction, right? So it's just the vector summation of those two, right? And so you can see that, well, it's going to be between those two, okay? And so then phi static, that's the angle of friction. As long as it is greater than the angle of the ramp, we're in good shape. This thing is self-locking, okay? Excuse me? R is the resultant of the normal and the force of friction. Okay? Because by getting the resultant, if we go way back to up here, right? By using R in this analysis, I'm able to get down to one equation. If I kept this as in the force of friction and the normal as separate pieces, then I would have more variables here and I couldn't get rid of it and come up with a nice equation. Okay? So R is just that resultant. So the question is, how do you know where normal and phi are? The theta is always going to be between normal and vertical. Phi is always between normal and the resultant. Okay? But what we can do, we could do our analysis, or we can look in the book, and they've already done a couple for us. So there's kind of two cases of downward impending motion. One is where the angle of friction is less than the angle theta. That means that this is not self-locking. It's going to slide down the ramp, and we have to put some moment or some force to hold it from going down the ramp. So this is a non-self-locking screw. Okay? In that case, we have that the moment required to keep it from going down is RW tan theta minus phi static. In the case where we have phi static is greater than theta, then we have to apply a moment to shove it down the ramp, which this is the case of our screw we're working on right now. And we have to say that the moment required to unscrew it would be RW tan phi static minus theta. That's a whole bunch of mumbo jumbo. Okay? What we've decided for this problem is that phi static is greater than theta. This tells us that this is a self-locking screw. Which means we need to apply a torque in order for it to unscrew. self-locking, meaning that it won't, if you stop applying, when we stop applying our 30 or our 120 inch-pounds of torque on the C-clamp, it's not going to just all unwind itself. It's going to stay right there. It's self-locking. Okay? So now, if we know this is true, the equation we use for when phi static is greater than the angle of the ramp is the moment is equal to R times the weight, tan, phi static minus theta. Okay? So we found that theta is 1.82, phi static is 11.3. We know our W is 2059. So let's do some substitution into this. The moment we need is going to be equal to the radius of the screw, which is 0.25, times the clamping pressure, 2059, times the tangent of phi static, which we found to be 11.3, minus 1.82, .86 inch-pounds. Joseph, you had a question, is the phi the same? Is that what you're asking? Yeah, so remember, where's phi come from? Phi is the inverse tangent of mu static, right? So it's just the coefficient of static friction, so it would be the same whichever direction you're going. Yeah. Although you could make a really cool screw, potentially, that had doesn't have a constant mu static, right? Why would you do that? Because maybe you want to lift a really heavy load, and you want it to be as easy as possible, but then you don't want it to unscrew itself. So if you made it so that it had a really small coefficient of static friction as you go thread in, right, versus a really high coefficient of static friction as you thread out, you could make it self-locking. Or even if you just had like ridges on it, you know. Why would you do what with the screw? How would you do that? Yeah, you'd have to do some sort of surface treatment, or you'd have to make the screw, like what if we made make it sawtooth? You know? So it's easier to push the block up the ramp than it is to push the block down the ramp. I don't know how you would actually manufacture that. Like, that's for you to figure out. I just come up with the ideas. I'm the visionary. You actually make them work. Yeah, sure. So 3D printing with metal could do that. Yep. So what did we find? We found that 86 inch-pounds is what's required to loosen the clamp after we've tightened it. Okay? You understand locking versus self-locking versus not? Kind of how that changes things? All right. How much time we got? Oh, we got time for you to do a problem here. Methinks. Let's do a Lally column. They're called Lally Columns. I don't know why they're called that, if it's the brand or what, but this is a Lally column. You'll see these in basements. They're more common in the Midwest than they are here. So in the basement of a house, they put in these columns that are adjustable, which is pretty freaking cool. So you can jack your whole house up if it sags. That's neat. Okay, so it says the column is used to support the upper floor. If a force of 80 newtons is applied perpendicular to the handle to tighten the screw, determine the compressive force in the column. The square threaded screw on the jack has a coefficient of static friction, mu static of 0.4. So what does this tell us? What does mu static tell us? Phi, right? Phi is going to be the tan inverse of that. The mean diameter of 25 millimeters and a lead of 3 millimeters. So in this case, when they tell you the lead, they're telling you the height of the ramp is 3 millimeters, okay? The length of the ramp, in this case, would be what? About 77 millimeters, right? 25 millimeters times pi. The lead is the height of the ramp. So the lead of a screw tells you for one revolution, how much do you move? It's like the pitch of a prop.
Is that common to have a jack for your house?
So it is. So is this common to have a jack for your house? Yes, it's common in basements to have these in many parts of the country. They're an adjustable column that you put in, and you can screw that. I mean, you kind of set it and forget it. Another place you would actually see this is if you look at when they're building high-rise buildings, like in downtown Portland, and they're pouring concrete floors. I don't know if you've ever noticed that, but like skyscrapers have concrete floors going all the way up. Well, how does that work? I mean, because they're suspended there, they have rebar or cables in them that tension those slabs so that they don't just fall in. But while they're curing, they have to be supported underneath. And so you'll see a ton of Lally columns that they just put in there that hold that floor up while it cures, while the concrete cures, and then they unscrew them and take them out. Okay? All right, so go ahead and do this. You got this. This is a pretty straightforward one. First, you can check, is this self-locking? I guess it actually doesn't matter. If you're asked to figure out, like, how much does it smash, if you're making it worse, it doesn't matter if it's locking or self-locking, doesn't make any difference. You're adding the two angles, the friction angle and the angle of the ramp, okay? Yep, you're trying to find the load on the column.
The height of the thread, right?
Yep, lead is the height of the thread. What's that? They are. Daniel, what'd you get for phi static and theta?
For the static, I got 21.8.
Okay.
Theta, I got 2.18.
So is this a lock? Is this a self-locking or not screw? How do you know it's self-locking? Because phi static is greater than theta. Most screws, I'd say, are self-locking. Okay. Because you have to get a really, really low coefficient of friction or a really, really high lead angle for it not to be self-locking. Okay. So most screws are self-locking. So then if we have these two values, we can figure out, we're smashing it, so we know the equation is M RW tan theta plus phi static, right? So the moment we know, we're given that it's 80 newtons at half a meter, right? And that is equal to 25 mean diameter of 25 millimeters. So that's going to be a radius of 12.5 millimeters, which is 0.0125, isn't it? Meters. You did what? Ah, yes, let's do that. I like that better. Instead of 0.5 meters, let's have this be 500 millimeters. And then we can make this 12.5 millimeters. W we don't know. Tangent of 21.8 plus 2.8. 2.18, sorry. Okay. And what do you get for W? 7 point what? 7.19 times 10 to the third newtons. Anyone else get that? About 7.2 kilonewtons. Okay. So just we're out of time, but let's go back through this. So what is M in this equation? So it's the moment applied to the screw. Okay, so the M is the amount of twist you're putting on the screw. Okay, what's R? Radius of the screw. Okay, what's W? It's the weight of the thing that you're moving with the screw, or it's the smashing force, right? It's the force that's along the axis of the screw. Okay, what is theta? Okay, so it is the angle between the normal and vertical. It's also the pitch of the screw, essentially, right? So this is this is the angle of the ramp. If we're saying that a screw is just a wedge wrapped around a circle, it's the angle of that wedge. And what's phi static? I call it the friction angle, right? So it's governed by the coefficient of friction, right? So it's the inverse tangent of the coefficient of friction. It's the angle between the normal force and the resultant also. But I just want you to be able to look at this equation and know what each of the pieces are, because I think that's all it takes to solve it. The equation itself is fairly simple. The moment applied, or the moment required, is going to be equal to the radius of the screw times the weight you're trying to support times the tangent of the angle of the ramp plus the angle of friction. Okay? All right. So if you have any other topics for me to cover besides these ones here, 3D equilibrium, non-rectangular distributed loads, moment about a specified axis, complicated frame or machine, or a couple moment, please email me so that I can prep them for Wednesday. All right?